Welcome to this session of Energy Conservation and Management. Myself, Anirban Sarkar, Assistant Professor in Mechanical Engineering Department of JIS College of Engineering, Kolkata. In today's session, we will start the Module 3, that is Total Energy Concept, CHP cycles and their applications. So today's session, we will discuss principle of cogeneration and its systems. Learning outcome: to understand the need for cogenerations, its principle and systems. First of all, we need to understand for cogeneration. The conventional method of power generation and supply to the customer is become wasteful in the sense that only a third of the primary energy fed into the power plant is actually made available to the user in the form of electricity. In conventional power plant, efficiency is only 35% and remaining 65% of energy is lost. The major source of loss in the conversion process is the heat rejected to the surroundings, water and air due to inherent constraints of different thermodynamics cycles employed in power generation. Also, further losses of around 10 to 15% are associated with the transmission and distribution of electricity in the electrical grid. In this figure, typical coal fire station, the total heat balance are shown. So for an input energy of 100 gigajoule, as it is fed into the boiler, the energy lost from the hot surface due to radiation, approximately it may be 1 gigajoule. And energy loss from the blowdown and leakage, that is estimated at 0.8 gigajoule. Next, the power transmitted to the steam turbine, that is available, energy in steam turbine is available, that is 87.3 gigajoule. While converting this part from the coal, the energy loss in the unburnt carbon in ash and dust, that is 0.7 gigajoule. And from the flue gas and dust removal, the energy losses to the stack due to heat taken by the flue gas, that is approximately 10.2 joule. So if we go for balance, that is a total 87.3 gigajoule estimated energy is available at the steam turbine as shown. Now, the generator output, that is 39 gigajoule, and remaining heat, that is going to the condenser. Condensate returned to boiler. The condensate water is again fed into the boiler. So in this process, electricity used by auxiliaries, that is approximately 2.8 gigajoule, and electricity to the system, that is 36.3 gigajoule. And in this process of cooling tower, which is the major energy losses during the process, that is 48.3 gigajoule. So in a conventional power plant, the thermal efficiency that is ultimately available at the rate at the electricity, that is 36.2, and input energy we have given 100 gigajoule. So that is 36.2 TBD. So the major losses in the typical coal-fired power station, that is the cooling tower or the condenser and cooling tower, that is estimated as, that is nearly half the energy is lost. And another major source of loss, that is from the flue gas. Next, so now we understand why we need the cogeneration. Because majority of the power losses in a conventional power plant, and only merely 35 to 36% of the energy is converted into the high-grade energy. Now, principles of cogeneration. Cogeneration or combined heat and power is defined as the sequential generation of two different forms of useful energy from a single primary energy sources. Typically, mechanical energy and thermal energy. Mechanical energy may be used either to drive an alternator for producing electricity or rotating equipment such as motor, compressor, pump, or fan for delivering various services. Thermal energy can be used either for direct process applications or for indirectly producing steam. Hot water, hot air for dryers, or chilled water for process. Cogeneration provides a wide range of technologies for applications in various domains of economic activities. The overall efficiency of energy use in cogeneration mode can be up to 85% and above in some cases. Cogeneration advantages. For example, in this figure shown, an industry requires 24 units of electrical energy and 34 units of heat energy. Those separate heat and power route, the primary energy input in power plant will be 60 units, assuming for the power station, that is 40% efficiency. If a separate boiler is used for steam generation, then the fuel input to the boiler will be 40 units, assuming the 85% efficiency. So now, if the plant has co-generated, then the fuel input will be only 68 units to meet the both electrical and thermal energy requirement. As in this case, the efficiency of this plant for cogeneration is taken as 85%. It can be observed that the losses, which were 42 units total in case of separate heat and power, has reduced to 10 units in cogeneration mode. Along with the saving fossil fuels, cogeneration also allows to reduce the emission of greenhouse gases, particularly carbon dioxide emissions. The production of electricity being on site, the burden of the utility network is reduced and the transmission line losses eliminated. Cogeneration makes sense from both macro and micro perspectives. At the macro level, it allows a part of financial burden of the national power utility to be shared by the private sector. In addition, indigenous energy sources are conserved. At the micro level, the overall energy bill of the user can be reduced, particularly when there is a simultaneous need for both power and heat at the site, and a rational energy tariff is practiced in the country. Next is technical opinions for cogenerations. Cogeneration technologies that have been widely commercialized, including extraction back pressure steam turbine, gas turbine with heat recovery boiler, with or without bottoming steam turbine, and reciprocating engines with heat recovery boilers. Cogeneration technology uses different combinations of power and heat producing equipments, which are numerous. Most widely used combinations are mentioned below. That is, first of all, steam turbine and fired boiler based cogeneration system. So the type may be, that is, the boiler may be coal or lignite fire plant. It may be liquid fuel fire plant. It may be natural gas fire plant, or it may be baggage or husk fire plant. The options for steam turbine, that is, maybe back pressure steam turbine we can use, extraction and condensing steam turbine, extraction and back pressure steam turbine. Next is gas turbine based cogeneration system. That is, it may be natural gas fire plant or liquid fuel fire plant. The waste heat recovery can be done by steam generating in unfired or maybe supplementary fired boiler or fully fired waste heat recovery boiler. It may be utilization of steam directly in process or utilization of steam power generation from steam turbine generation. That is cogeneration cum combined cycle. And absorption chiller, utilization of heat for direct heating. Third, that is reciprocating engine based cogeneration system. Reciprocating engine may be liquid fuel fire plant or maybe natural gas fire plant. The waste heat recovery may be done by steam generation in unfired or supplementary fired waste heat recovery boiler. It may be used waste heat recovery. Waste heat may be recovered by absorption chillers, and may be utilization of steam directly in process or utilization of steam for direct heating purposes. Cogeneration technology. A proper selection of cogeneration system configuration from a few basic system cogeneration described makes it feasible to produce fast either electrical energy or thermal energy. First of all, that is the cogeneration technology, steam turbine based cogeneration system. Number 2, gas turbine based cogeneration system. Number 3, combined system, that is gas turbine based cogeneration, that is steam or gas turbine based cogeneration system. And number 4, reciprocating engine based cogeneration system. Most widely used cogeneration system in the chemical process industrial plant are based on steam turbine, gas turbine or combined steam gas turbine configuration with installation based on reciprocating engine configuration in moderate number. These configurations are widely accepted by the industries due to their proven track record and easy commercial availability of required equipment. The cogeneration system based on Stirling engine concept is still under development and hence not described in this session. All combinations of cogeneration systems are based on first and second law of thermodynamics, basic concept of possible different cogenerations configuration system consisting of primary energy sources, a prime mover driven electric power generator, and arrangement of use the waste heat energy rejected from the prime mover are briefly described along with system schematic diagrams. So first of all, there is steam turbine cogeneration system. This system works on the principle of Rankine cycle of heat balance. In Rankine cycle, the fuel is first fired in a suitable boiler to generate high pressure steam at predetermined parameters. The steam so produced is then expanded through a steam turbine to produce mechanical power, electricity, and low pressure steam. The steam turbine could be of back pressure type, extraction cum condensed type, or extraction cum back pressure type, depending on different levels and parameters at which the steam is required by the chemical process in that particular plant. Cogeneration system with back pressure steam turbine is schematically represented in this figure. In a conventional fossil fuel fired power plant, maximum fuel efficiency is about 35% is achieved. Maximum heat loss occur by way of the heat rejected in a steam condenser, where a straight condensing steam turbine is used. Some improvement in the efficiency could be attained through extraction cum condensing steam turbine instead of straight condensing type as shown in this figure. The steam so extracted could be supplied to either process consumer or to heat the feed water before it enters into a boiler. As seen from above, the rejected heat energy from the steam turbine is most efficiently used to meet the thermal energy requirement of that particular chemical process by adopting non-condensing steam turbine based cogeneration system. The overall efficiency of around 80 to 85% is achieved in this type of plant configuration. The selection of steam turbine for a particular cogeneration application depends on process steam demand at one or more pressure temperature levels. The electric load to be driven, power and steam demand variation, essentiality of steam for process, etc. The steam to power ratio also plays a role in selection of steam turbine. Generation of very high pressure steam and low back pressure at steam turbine exhaust would result into small steam to power ratio. Smaller value of ratio would indicate the lower utilization value of steam for heating or process purpose. The flexibility in steam to power ratio can be obtained by using steam turbine with regulated extraction. Steam turbine based cogeneration system can be fired with variety of fossil fuels like coal, lignite, furnace oil, residual fuel oil, natural gas or conventional fuels like biogas, baggage, municipal waste, husk, etc. Hence, the fuel flexibility for this type of system is excellent. However, this configuration is not recommended for smaller installation as it is more expensive and maintenance oriented. It is also not feasible to adopt this system if the chemical industry is located nearer to a populated area, as it becomes major source of environmental pollution depending upon type of fuel used, that is coal, lignite or furnace oil. Next, that is number 2, gas turbine cogeneration system. This type of system works on basic principle of Brayton cycle of thermodynamics. Air drawn from the atmosphere is compressed and mixed in a predetermined proportion with the fuel in a combustion, in which the combustion takes place. The flue gases with a very high temperature from the combustor are expanded through a gas turbine, which drives electric generator and air compression. A portion of mechanical power is used to compress the combustion air. The balance is converted into electric power. The exhaust flue gases from the gas turbine, typically at high temperature, that is ranges of 480 to 540 degrees centigrade, act as a heat source from which heat is recovered in the form of steam or hot air for any desired industrial applications. Industrial gas turbine based power plant installed to generate only electric power operate at the thermal efficiency of 25 to 35% only, depending on the type of size and gas turbine. Aerodeviative gas turbine operates at marginal higher efficiency than the conventional industrial heavy duty machine. With recovery of heat in exhaust flue gases in a waste heat recovery boiler or heat recovery steam generator to generate the steam, overall plant efficiency of around 85 to 90% is easily achieved. As an alternative, the heat of exhaust flue gas can also be diverted to heat exchanger to generate hot water and hot air instead of generating steam. Compared to steam turbine based cogeneration system, the gas turbine based cogeneration system is ideal for the chemical process industries where the demand of steam is relatively high and fairly constant in comparison to that of steam. Gas turbine based cogeneration system gives a better performance with clean fuels like natural gas or non-ash bearing or low ash bearing liquid hydrocarbons fuels like naphtha, high speed diesels, etc. Though high ash bearing hydrocarbon based fuel like fuel oil, crude oil or residual fuel oil can also be fired in the gas turbine, but with some inherent problem like frequent cleaning of gas turbine, more maintenance and spares, etc. Another major drawback is that when demand of power drops below 80% of gas turbine capacity, the specific fuel consumptions increases and the steam output from waste heat recovery boiler also drops. The steam output can be maintained by restoring to a supplementary fuel firing in waste heat recovery boiler. The burners for supplementary firing are generally installed in the exhaust flue duct provided between the gas turbine and waste heat recovery boiler, and are designed to enable waste heat recovery boiler to maintain full steam output even when the gas turbine is partly loaded. This system ensures a high flexibility in design and operation of the plant, as it is possible to widely vary ratio of steam to power loads without very much affecting the overall plant efficiency. In case of exhaust duct-based supplementary firing, the fuel requirement is substantially reduces proportionate to additional steam generated due to presence of about 15% hot unburned oxygen in exhaust flue gases. If supplementary firing is not provided, it is become a simple cogeneration system consisting of gas turbine generator and waste heat recovery boiler. Number 3, combined steam gas turbine based cogeneration system. It is clear from the title that the system itself that is work on the basis of combination of both Rankine and Brayton cycle, and hence it is called combined steam gas turbine based cogeneration system. In this system, fuel energy is first utilized in operating the gas turbine as described in gas turbine based cogeneration system. Waste heat of high temperature exhaust flue gases from the gas turbine is recovered in waste heat recovery boiler to generate high pressure steam. This high pressure steam is expanded through a back pressure steam turbine or an extraction cum back pressure steam turbine or an extraction cum condensing steam turbine to generate some additional electric power. The low pressure steam available either from the exhaust or back pressure steam turbine or from extraction is supplied to the process consumer. Such combination of two cycles gives a definite thermodynamic advantage with very high fuel utilization factor under various operating conditions. When the ratio of electric power to thermal load is high, the cogeneration plant based on combined cycle principle provides better results than the plant based on only back pressure steam turbine due to availability of additional power from steam turbine besides low pressure steam. Without firing of any extra fuel, if supplementary firing is restored to waste heat recovery boiler as mentioned in case of gas turbine based system, to maintain steam supply during low load of gas turbine. The operational flexibility of such plants can be brought nearer to extraction cum condensing steam turbine. The process in which the demand of electricity remains very high even when the demand of steam is very low. Then extraction cum condensing steam turbine can be used instead of back pressure steam turbine. The control concept is similar to that as mentioned above. Expect that the steam turbine generator also participate in control of electrical output. The process steam is controlled by steam turbine bypass valve. In case of zero process steam output, the control range of electric power output is extended by allowing almost total steam exhaust from steam turbine to go to the condenser for that particular duration. Process steam requirement at different parameters can also be satisfied in combined cycle system by installing either a condensing steam turbine with double extraction or a back pressure steam with one or two extraction. Combined gas cum steam turbine type based cogeneration achieves overall plant efficiency of around 90% with optimal fuel utilization. In addition to this, the combined cycle plants are most economical in many cases due to very low heat rates, low specific capital cost of gas turbine plant, and availability of power from open cycle operation of gas turbine plant, as it requires lesser time for erection. Major drawback of this system is less fuel flexibility as in case of gas turbine based cogeneration system. Number 4, reciprocating engine cogeneration system. In this system, the reciprocating engine is fired with fuel to drive the generator to produce electrical power. The process steam is then generated by recovery of waste heat available in engine exhaust in waste heat recovery boiler. The engine jackets, cooling water, heat exchanger, and lube oil cooler are other source of waste heat recovery to produce hot water or hot air. The reciprocating engines are available with low, medium, and high speed variations with efficiencies in the range of 35 to 42%. Generally, low-speed reciprocating engines are available with high efficiencies. The engines having medium and high speeds are widely used for cogeneration applications due to higher exhaust flue gas temperature and quality. When diesel engines are operated along for power generation, a large proportion of fuel energy is rejected via exhaust flue gas. In cogeneration cycle, particularly all the heat energy in engine jacket, cooling water, and lube oil cooler, and substantial proportion of heat is exhaust gases is recovered to produce steam or hot water. With this, the overall system efficiency of around 65 to 75 is achieved. The heat rates of reciprocating engine cycles are high in comparison to that of steam turbine and gas turbine based cogeneration system. This system is particularly suitable for applications requiring a high ratio of electric power to steam, waste heat recovery boiler process of customer. Reciprocating engine can be fired only with hydrocarbon based fuel such as high speed diesels, light diesel oil, residual fuel oil, natural gas, etc. The engines are developed in which natural gas is also directly can fire. In view of lower overall fuel efficiency as mentioned above, this system is not economically better placed compared to the steam turbine or gas turbine based cogeneration system, particularly where power and steam are continuously in demand. Further to above, diesel engines are more maintenance oriented and hence generally preferred for operating intermediately or as a standby emergency power source. These are major drawbacks preventing widespread use of diesel engine based cogeneration systems. With this, today's session we are likely to conclude. These are the references. Thank you for joining this session.